For more than a century, physicists have tried to answer one of the most fundamental questions in science. What is mass? At first glance, the answer seems obvious. Mass is what gives an object weight, mass is what creates gravity, and mass is what resists acceleration. Everything around us, from a grain of sand to the largest galaxy, obeys these simple rules. They're so deeply rooted in our understanding of reality that we rarely stop to question them. But what if one of the most basic assumptions in physics was incomplete? What if nature allowed something that appears impossible? Not antimatter, not dark matter, but something even stranger. Negative mass. At first, the idea sounds absurd. How could mass be negative? How could something fall upward? How could gravity push instead of pull? For decades, these questions belonged almost entirely to the realm of speculation. Yet a handful of physicists have argued that dismissing the concept too quickly might be a serious mistake, and among them is French astrophysicist Jean-Pierre Petit. To understand why he believes negative mass could change everything, we first need to understand what his model is trying to accomplish. Petit is best known for developing the Janus cosmological model, which, unlike the standard cosmological model, proposes that the universe is composed of two coupled sectors. One contains the ordinary positive mass matter we know, stars, planets, galaxies, and ourselves, while the other contains negative mass matter. According to Petit, these two sectors coexist while remaining largely invisible to one another, and their gravitational interaction could explain phenomena that modern cosmology currently attributes to dark matter and dark energy. Whether this model is correct remains an open scientific question, and most physicists do not accept it, as it remains outside the scientific mainstream. But one thing is undeniable: the model is intellectually ambitious. Because if negative mass really exists, then its implications extend far beyond cosmology and reach into one of humanity's oldest dreams: traveling to the stars. In our previous documentary, we explored one remarkable consequence of the Janus model. According to Jean-Pierre Petit, a spacecraft traveling through the negative mass sector could experience dramatically different geometric conditions. Distances could effectively become 100 times shorter, and the characteristic speed associated with that sector could become 10 times greater. Combined together, these two effects would reduce travel time by a factor of 1,000. It is one of the most fascinating ideas ever proposed for interstellar travel. But there is an obvious problem. How do you get there? How could a spacecraft built from ordinary positive mass matter ever enter a negative mass sector? That question leads us to what may be the most speculative and perhaps the most fascinating part of Jean-Pierre Petit's work: the inversion of mass. According to Petit, the greatest challenge is not building a faster engine, it is changing the sign of the spacecraft's mass itself. At first, this sounds impossible, because mass is not like electrical charge. You cannot simply flip a switch and transform positive into negative. Or can you? During one of his discussions with Idris Aberkane, Jean-Pierre Petit described an idea that had been shared with him years earlier through technical exchanges with American researchers. He did not present it as an established technology, nor as something demonstrated experimentally, but rather as a possible physical mechanism, a hypothesis, a pathway that might one day make such a transition conceivable. And surprisingly, the story does not begin with spaceships. It begins inside the atomic nucleus. To understand why, we need to introduce a concept that rarely appears outside nuclear physics: the metastable state. When an atom absorbs energy, it usually does not keep that energy for very long. Within an incredibly short time, it releases the excess energy and returns to its lowest energy configuration. This process happens constantly throughout the universe, in stars, in lightning, in radioactive decay, as everything seeks stability. But nature sometimes behaves differently. Certain atoms, and more importantly, certain atomic nuclei, can become trapped in what physicists call metastable states, where instead of releasing their energy almost immediately, they can hold on to it for much longer, sometimes milliseconds, sometimes seconds, and in rare cases, even hours. Jean-Pierre Petit illustrates this idea by recalling his own research, noting that during his doctoral work, he used metastable helium, whose excited state survives much longer than ordinary excited atoms. For him, this demonstrates an important principle. Energy does not always have to disappear immediately, and under the right conditions, nature can store it. And according to Petit, this is where things become truly interesting. Because if enormous quantities of energy could be concentrated inside metastable nuclear states, perhaps that stored energy could eventually be used for something extraordinary, not to power an engine, not to produce electricity, but to modify the very properties of matter itself. This is where his hypothesis takes an unexpected turn. Petit explains that the proposed mechanism would require injecting tremendous amounts of energy directly into atomic nuclei, not into the spacecraft as a whole, and not into its engines, but into the nuclei themselves. The challenge, of course, is obvious. How do you deliver such extraordinary amounts of energy with sufficient precision? According to the explanation Petit recounts, one possible answer lies in an extremely ambitious technology: gamma-ray lasers. Unlike the visible lasers we use today, gamma-ray lasers would operate at enormously higher photon energies. Such devices remain highly speculative and extraordinarily difficult to build, and no publicly available technology has demonstrated this capability. Yet Petit notes that research into high-energy gamma systems has existed for decades. His argument is not that these systems already perform mass inversion, but rather that if such lasers could one day exist, they might allow energy to be focused into metastable nuclei with extraordinary precision. And if that became possible, then perhaps the sign of mass itself might no longer be immutable. This is the point where conventional physics and Jean-Pierre Petit's vision begin to diverge. For mainstream physics, no demonstrated mechanism exists to reverse the sign of an object's mass. For Petit, however, this possibility deserves to be explored, not because it has been proven, but because if it were possible, everything else in the Janus framework would suddenly become physically meaningful. The spacecraft would no longer remain confined to our familiar positive mass sector and could, at least in principle, undergo a transition into the second sector described by the Janus model. And once that transition occurred, the journey itself would become something entirely different. If Jean-Pierre Petit is correct, then mass inversion would not simply represent another scientific discovery. It would redefine humanity's place in the universe. Because for the first time, interstellar travel would no longer depend exclusively on propulsion. It would depend on geometry. Imagine a spacecraft that successfully undergoes the transition Petit describes. From the outside, observers might see something extraordinary. The spacecraft would no longer behave according to the familiar rules governing ordinary matter. According to the Janus model, it would now belong to another gravitational sector, not another galaxy, not another dimension in the science fiction sense, but another sheet of the same universe, a hidden companion that has always existed alongside our own. If that transition were possible, the consequences would be astonishing. The stars themselves would not move, and the galaxy would not become physically smaller. Instead, the traveler would experience a completely different geometric landscape. In previous discussions, Jean-Pierre Petit explained that distances within this second sector could effectively become 100 times shorter. Think about that for a moment. Imagine standing in Paris and wanting to reach New York, but instead of crossing the Atlantic Ocean, the geography itself changes. The destination remains identical, but the path connecting the 2 points suddenly becomes dramatically shorter. You have not increased your speed, you have changed the map. Petit argues that something similar could happen on a cosmic scale, and according to his interpretation of the Janus framework, The characteristic propagation speed associated with this second sector could also become approximately 10 times greater than the speed limit observed within our own. Again, this remains a speculative component of the model and has not been experimentally demonstrated. But if both effects existed simultaneously, the implications become extraordinary. Distances reduced by 100, characteristic speed increased by 10, and travel time reduced by 1,000. Suddenly, the impossible begins to look surprisingly different. A voyage requiring 1,000 years could, in principle, become a journey lasting only a single year, not because Einstein had been defeated, but because the traveler would no longer be following the same geometric path. This distinction is essential. Jean-Pierre Petit does not argue that spacecraft should accelerate infinitely. He argues that they may eventually travel through a different geometric framework. And if that sounds revolutionary, it is because it challenges one of the deepest intuitions we possess, that distance is absolute. Perhaps it is not. Perhaps distance itself depends upon the structure through which one travels. But this raises another fascinating question. If such transitions became possible, who else might already know how to perform them? For decades, astronomers have wondered why the universe appears silent. The Milky Way contains hundreds of billions of stars, many possess planets, and some almost certainly possess conditions favorable to life. If intelligent civilizations are common, where is everybody? This puzzle is known as the Fermi paradox, and many explanations have been proposed. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations destroy themselves before reaching the stars. Perhaps they simply have no desire to explore. Jean-Pierre Petit's ideas suggest another possibility. Perhaps advanced civilizations eventually discover aspects of reality that we have not yet understood. Perhaps they stop thinking in terms of engines and begin thinking in terms of geometry. And perhaps the true revolution in space exploration is not propulsion, but topology, gravitation, and the hidden architecture of reality itself. Whether this vision is correct remains unknown. No experimental evidence currently demonstrates that mass inversion can occur. No spacecraft has ever publicly entered another gravitational sector, and no laboratory has announced the successful reversal of the sign of mass. These ideas remain speculative, and it is important to say so clearly. Science advances through evidence, not belief, and every hypothesis must ultimately confront experiment. The Janus model is no exception, yet history teaches us another lesson. Progress often begins with questions that appear impossible. Flying was impossible, leaving Earth was impossible, landing on the moon was impossible, and every generation inherits limits that the next generation eventually challenges. Does that mean mass inversion will one day become reality? Nobody knows. Perhaps future experiments will show that the idea cannot work, and perhaps new discoveries in fundamental physics will reveal mechanisms nobody has yet imagined. That is precisely why ideas like these deserve careful examination rather than immediate dismissal, not because they are necessarily correct, but because they force us to ask better questions. And perhaps that is Jean-Pierre Petit's greatest contribution, beyond equations, beyond cosmological models, beyond controversies. He invites us to reconsider assumptions that have become so familiar we rarely notice them anymore. Must gravity always behave exactly as we expect? Must mass possess only one sign? Must the universe contain only one visible sector? Must interstellar travel remain forever impossible? These are uncomfortable questions, but science has always progressed by confronting uncomfortable questions. Perhaps the answers will confirm everything we already believe, or perhaps they will surprise us. For now, we simply do not know. What we do know is that the universe continues to challenge our imagination again and again. And perhaps the greatest discoveries of tomorrow will not come from building larger rockets, but from understanding reality itself more deeply. Because if Jean-Pierre Petit is even partially correct, The next giant leap for humanity may not begin with a launch pad. It may begin inside an atomic nucleus, inside a tiny metastable state illuminated by an extraordinary burst of gamma radiation. And from that microscopic event, an entirely new pathway through the cosmos could one day emerge. Whether that future ever becomes reality remains uncertain. But one thing is already certain. As long as questions like these continue to be explored, our journey toward understanding the universe is far from over.